There's a question that has lived quietly at the edge of astronomy for as long as anyone has been looking up. It is not the kind of question that gets answered in a single paper or a single decade of careful observation. The question sits between two numbers, and the distance between those numbers is the size of the unknown itself. The first number is enormous in a way that resists ordinary comprehension, even when you hold it directly in your mind. Current estimates place tens of billions of planets in habitable zones across the Milky Way alone, worlds where the conditions for liquid water could in principle exist. Extend that count across the observable universe, with its hundreds of billions of galaxies, and the figure climbs into quintillions, a word that functions more as a gesture than a quantity. The second number is the count of worlds where life has been directly and unambiguously confirmed to exist. That second number is exactly 1. The one world is this one, the one you are resting on tonight. The gap between those two figures is what we are here to sit with. The catalog that lives inside that gap is not a short one, and it is growing every month as instruments improve and methods sharpen. More than 6,000 planets around stars other than our Sun have now been positively confirmed, with a candidate count several times higher still waiting on formal verification. Inside that larger collection, a quieter subset has emerged over the past 2 decades of searching. These are the worlds that orbit at just the right distance from their host stars, close enough to be warm, far enough to avoid being scorched, sitting in the narrow band where water might pool on a surface and stay there. A smaller subset within that subset is composed of worlds dense enough and compact enough to be genuinely rocky rather than gaseous. From those structured numbers, a patient and slightly unsettling question has taken shape, one that the field has been building toward for a generation. Which of those worlds, right now, tonight, without our knowing it, might already be alive? That question does not have an answer yet. But the catalog of candidates is real, and each entry in it deserves to be held as a place rather than a statistic. That is what the next several hours are for. A note before the names begin, because the distinction matters more than it might first appear. A habitable world and an inhabited world are not the same thing, and the difference between them is the difference between possibility and fact. The first asks whether a planet carries the architectural conditions under which life, as we understand, it could plausibly survive and persist. The second asks whether life is actually present, whether something is swimming or crawling or photosynthesizing in whatever ocean or atmosphere that world possesses. The first question can be partially answered by observation, by measuring orbital distances and planetary sizes and atmospheric compositions from across light years of space. The second requires either a direct detection of biological chemistry in a planet's atmosphere or eventually a probe close enough to sample it directly. Popular coverage tends to blur the line between these two questions, and the blurring does real damage to how clearly we can think about what we know. Tonight, the line stays visible. A habitable world is a world where life could exist. An inhabited world is one where it does. The named candidates in the catalog are the places where the question becomes specific enough to hold in the mind as something more than a number. There is Kepler 22b, sitting roughly 620 light-years away in the constellation Cygnus, the first habitable zone world ever confirmed around a star closely resembling our own Sun. There is Proxima Centauri b, orbiting the nearest star to the solar system at a distance of just 24 light-years, close enough that on a cosmic scale, it is practically next door. There is the TRAPPIST-1 system, a compact and resonant architecture of 7 Earth-sized rocky planets orbiting a dim ultra-cool dwarf star less than 40 light-years away, 3 of them sitting inside the habitable zone simultaneously. There is Kepler 452b, sometimes called Earth's older cousin, orbiting a Sun-like star on nearly the same annual schedule Earth keeps, but around a star more than 1 billion years older than ours. There is K2-18b, a sub-Neptune world 124 light-years away, with a hydrogen-rich atmosphere and the faint chemical signatures that have begun to make it one of the most closely watched objects in modern astronomy. Each of these worlds has a name, and a name changes how a thing can be thought about. A name makes a place out of a number. The population behind those named entries is where the scale becomes difficult to hold. Current best estimates suggest that somewhere between 30 and 80% of all Sun-like stars in the galaxy host at least one Earth-sized planet in their habitable zone. Apply even the conservative end of that range to the 400 billion stars of the Milky Way, and the result is tens of billions of plausibly habitable worlds in our galaxy alone. Apply it across the observable universe, and the figure moves in a territory where the words themselves stop functioning as measurements and start functioning as placeholders for something too large to feel. The galaxy is, by the simplest reading of the available evidence, full of places where the conditions for life could exist. The universe is almost certainly fuller still. That is the headline answer. And it is also only the beginning of the question, because the headline answer says nothing about whether any of those worlds are actually alive. What draws people to this question is not purely the science, though the science is extraordinary enough on its own terms. It is the specific texture of the not knowing, the fact that the answer could be almost anything within a range that spans from 1 to quintillions. We might be the only inhabited world in a galaxy of tens of billions of habitable ones. A single lit window in an otherwise dark building of almost incomprehensible size. Or life might be so common that the galaxy is essentially saturated with it, and our isolation is simply a matter of distance and the speed of light and the brevity of the time we have been listening. Both of those possibilities are, right now, consistent with everything we know. The instruments that could begin to distinguish between them are either already in space or currently under construction. The answers are coming, but they are coming slowly, and the question will outlast this night by years or decades. That slowness is part of what makes the catalog worth sitting with at this hour, when there is no urgency and no deadline, and the only task is to let the scale of the thing settle. The toolkit that built the catalog is worth understanding briefly, because the way we know what we know shapes how much confidence to place in it. Four detection methods are doing most of the work. The transit method watches for the tiny periodic dimming of a star's light when a planet crosses in front of it, yielding the planet's size and orbital period with high precision, but only when the geometry lines up correctly. The radial velocity method measures the small Doppler shifts in a star's spectrum caused by the gravitational tug of an orbiting planet, yielding mass information that the transit method alone cannot provide. Direct imaging physically separates a planet's light from its host star, currently feasible only for large young worlds at wide separations, but the method of the future for nearby Earth analogs. Gravitational microlensing catches planets by the brief amplification of background starlight when a foreground star and its planetary system pass in front, revealing cold and free-floating worlds that the other methods largely miss. Each method has its own blind spots and biases, and the catalog reflects those biases in ways that require careful statistical correction before the numbers can be trusted at the population level. Astronomers are not counting habitable worlds directly. They are counting the detectable ones and then reasoning carefully about the rest. The definition of habitability that most of the catalog uses is worth holding clearly before the names begin. A world is considered habitable if, given an Earth-like atmosphere and reasonable surface pressure, liquid water could persist on its surface across geological timescales. The definition is doing quiet work on three fronts simultaneously. It uses liquid water as a proxy for the conditions that life on Earth requires, which is the only life we have as a reference point. It requires that the water be present at the surface rather than buried beneath kilometers of rock or ice. And it requires persistence across billions of years, not merely a warm moment in an otherwise frozen or scorched history. This is the conservative definition, the one most often invoked when the press reports a new potentially habitable world. It is not the only definition in use, and later in the catalog we will return to the softer and broader versions that expand the count in their own ways. For now, it is the working frame, and it is the one that gives the headline number its shape. The habitable zone is in the cleanest available shorthand, the right address without any guarantee about what is inside the envelope. A planet can sit squarely in the habitable zone and still be uninhabitable for a dozen independent reasons that have nothing to do with its distance from its star. It can lack an atmosphere entirely, leaving the surface exposed to radiation and temperature swings no biology could survive. It can have an atmosphere so thick that the greenhouse effect runs away and the surface becomes hot enough to melt metal. It can be tidally locked, with one hemisphere permanently baked and the other permanently frozen, requiring a specific kind of atmospheric heat transport to create any livable middle ground. It can lack a magnetic field, allowing its host star's wind to strip its atmosphere away over geological time, the way Mars lost its own air billions of years ago. It can lack plate tectonics, removing the carbon cycle that acts as a planetary thermostat across billions of years of stellar brightening. The habitable zone is the necessary first condition. It is nowhere near the sufficient one. The catalog of named candidates lives in the space between those two facts, and that is where the interesting questions are. Let your shoulders soften now. Let the day that brought you here begin to release its hold on your attention. The catalog is real, and it is large, and it is full of specific places that deserve to be thought about slowly rather than quickly. Over the next several hours, we will walk through the named worlds one by one, from the first habitable zone planet ever confirmed around a sun-like star to the most recently characterized atmospheric candidate, from the nearest potentially habitable world to the most Earth-similar world, yet detected by size and temperature. We will hold the population estimates and the conditional probabilities and the long silence of the radio telescopes alongside the names. We will not resolve the central question tonight, because it has not been resolved yet, and honesty about that is part of what makes the question worth taking seriously. What we will do is sit with the catalog in its current state, as it actually exists tonight, incomplete and growing and full of possibilities that the next 2 decades of observation may begin to answer. Let the night settle around you. Let her breathing slow. The first name in the catalog is already waiting. The first name in the catalog arrived through a method worth understanding before the place itself can be properly held. 4 distinct techniques have built the inventory of confirmed worlds that astronomy now maintains, and each one sees a different slice of what is actually out there. The transit method watches a star's brightness over time, looking for the faint periodic dimming that signals a planet crossing the face of its host. The radial velocity method reads the subtle Doppler shifts in a star's spectrum, the tiny blueward and redward wobbles caused by an orbiting planet's gravitational pull. Direct imaging physically separates a planet's own light from the overwhelming glare of its star, a technically demanding feat that current instruments can manage only for the largest and hottest worlds at wide orbital separations. Gravitational microlensing catches the brief amplification of background starlight when a foreground star and its planets pass in front, revealing cold and distant worlds that the other methods largely cannot reach. Each technique has its own geometry, its own sensitivity range, and its own particular blind spots. The transit method, for instance, only works when a planet's orbital plane happens to be oriented nearly edge-on from Earth's perspective, which is true for a small fraction of all planetary systems. The radial velocity method favors massive planets orbiting close to bright stars, because those combinations produce the largest and most measurable stellar wobbles. The result is a catalog that reflects not just what is out there, but what current instruments are capable of seeing, and those two things are meaningfully different. Understanding the difference is the first step toward trusting the numbers at the right level of confidence. The transit method has produced most of the confirmed catalog, largely through 2 dedicated space-based instruments that spent years staring at fixed fields of stars. A Jupiter-sized world crossing the face of a Sun-sized star dims the starlight by roughly 1%, a signal strong enough to detect reliably from the ground under good conditions. An Earth-sized world crossing the same star produces a dimming of only about 1/100th of 1%, a signal so faint that it required space-based photometry to measure with any consistency. The Kepler Space Telescope, launched in 2009 and retired in 2018, stared at a single patch of sky containing roughly 150,000 stars and recorded the brightness of every one of them continuously for years. The Transiting Exoplanet Survey Satellite, known as TESS, launched in 2018 and covers nearly the entire sky in a rolling sequence of observation windows, focusing on stars close enough to Earth for follow-up characterization. Together, these two instruments have produced the majority of the more than 6,000 confirmed exoplanets now in the catalog. The transit method yields two quantities with high precision: the planet's orbital period, derived from how often the dip repeats, and the planet's radius, derived from how deep the dip goes relative to the star's size. What does not directly yield is mass, which requires either radial velocity follow-up or transit timing variation analysis. Without mass, the planet's density and therefore its likely composition remain uncertain, a limitation that matters considerably when the question is whether a world is rocky or gaseous. The radial velocity method fills that gap in a way that depends on a different physical principle entirely. Every planet orbiting a star pulls that star gravitationally, causing both bodies to orbit their shared center of mass rather than the planet orbiting a perfectly stationary star. For a massive planet like Jupiter, the Sun's resulting motion reaches a peak velocity of about 13 meters per second, a speed roughly equivalent to a brisk jogging pace. For an Earth-mass planet at Earth's orbital distance, the induced stellar motion is only about 9 centimeters per second, slower than a leisurely walk across a room. Modern spectrographs are now approaching the precision needed to detect shifts that small, though the technical challenges involved are considerable and stellar noise remains a limiting factor. The method yields the planet's minimum mass rather than its true mass, because the orbital inclination relative to Earth's line of sight is not directly measured, and a face-on orbit would produce no detectable Doppler shift at all. Statistical corrections averaged over all plausible inclinations typically push the inferred true mass to about 15 or 20% above the measured minimum, a modest and well-understood correction. Combined with a radius from the transit method, the mass from radial velocity yields a bulk density, which in turn constrains the planet's likely composition in a way that neither measurement alone can accomplish. A world with a density near 5 or 6 grams per cubic centimeter is almost certainly rocky, like Earth or Mars. A world with a density near 1 or 2 grams per cubic centimeter almost certainly has a substantial envelope of gas or ice or water. The density is not a complete picture, but it is the most important single number for deciding whether a habitable zone planet is worth taking seriously as a rocky world candidate. Direct imaging and gravitational microlensing occupy the edges of the detection landscape, reaching places the first two methods cannot easily access. Direct imaging is currently limited to young, massive, widely separated planets whose own thermal emission is bright enough to be distinguished from the host star's glare using coronagraphs and adaptive optic systems. The technique will become far more powerful with the next generation of large space-based observatories specifically designed to suppress stellar light, and it is the method that will eventually yield atmospheric spectra of nearby Earth analogs around Sun-like stars. Microlensing works by a completely different mechanism, requiring a chance alignment between a foreground star and a background star as seen from Earth, with the foreground star's gravity briefly amplifying the background star's light in a characteristic way. Any planet around the foreground star leaves a secondary signature in that amplification curve, one that can be detected even for cold, distant worlds far beyond their host star's habitable zone. The method has revealed that free-floating rogue planets, worlds with no host star at all, may be extraordinarily common in the galaxy, possibly outnumbering stars by a factor of several. Its limitation is that the alignment is a one-time event, and the system cannot be revisited once the geometry has passed. Each of the four methods is in this sense a different kind of net, and the catalog is the sum of everything caught by nets with different mesh sizes dragged through different depths of the same ocean. The population that no net has yet reached is almost certainly larger than the population already cataloged, and the statistical work of inferring that unseen population from a seen one is where the headline numbers about tens of billions of habitable worlds actually come from. The working definition of habitability that underlies the catalog structure is precise enough to be useful and honest enough to carry its own limitations visibly. A planet is considered potentially habitable if, given an Earth-like atmosphere and a surface pressure comparable to Earth's, liquid water could persist on its surface across geological timescales measured in billions of years. The definition uses liquid water as its central proxy because water is the medium in which all known biochemistry operates, and because water's physical properties, its thermal range, its solvent capacity, its behavior under pressure, make it uniquely suited to the chemical complexity that life requires. The surface requirement distinguishes this definition from the broader class of subsurface ocean habitability, which will be addressed later in the catalog, but which operates under different physical assumptions. The geological persistence requirement excludes worlds that might have been briefly warm during some early energetic period, but have since frozen or scorched into permanent uninhabitability. Together, these three criteria produce the conservative habitable zone, the orbital band around any given star where these conditions could plausibly be met. The conservative zone for our own sun runs from roughly 0.95 astronomical units, just inside Earth's current orbit, to roughly 1.37 astronomical units, well past Mars but short of the asteroid belt. Earth at 1 astronomical unit sits comfortably near the middle of this range, which is either a reassuring confirmation that the definition is calibrated correctly or a reminder that the definition was built around the one example we have, depending on how carefully you hold the circularity. The inner and outer edges of the habitable zone are set by two distinct physical processes, each of which represents a way that a planet can fail the liquid water test catastrophically and permanently. The inner edge is defined by the runaway greenhouse limit, the point at which a planet absorbs enough stellar energy that water vapor begins to accumulate in its atmosphere faster than it can be removed. Water vapor is itself a potent greenhouse gas, so its accumulation traps additional heat, which evaporates more water, which traps more heat, in a positive feedback loop that has no stable equilibrium. At some critical distance from the star, the cycle becomes self-sustaining. The oceans boil away into the atmosphere over geological time, and ultraviolet radiation from the star eventually breaks the water molecules apart and allows the hydrogen to escape to space. The planet ends with a dry, dense, lethally hot surface and an atmosphere dominated by whatever gases were not lost to space, a description that fits Venus almost precisely. The outer edge is defined by the maximum greenhouse limit, the point at which even a carbon dioxide-rich atmosphere cannot maintain surface temperatures above freezing. As a planet cools, it requires more atmospheric carbon dioxide to maintain liquid water at the surface, but at sufficiently low temperatures the carbon dioxide itself begins to condense out of the atmosphere as dry ice, collapsing the greenhouse effect rather than sustaining it. Mosh, sitting on 52 astronomical units from the Sun, shows clear geological evidence of ancient river channels and lake beds, suggesting it once sat inside or near the outer edge of the habitable zone before its thin atmosphere and weak magnetic field allowed the surface water to be lost over billions of years. Of the 3 rocky planets in our solar system's temperate region, one worked, one failed at the inner edge, and one failed at the outer edge, which is either a sobering statistic or a useful calibration, depending on how you approach the question. The optimistic habitable zone widens both boundaries by using empirical evidence from Venus and Mars rather than strict theoretical limits. If Venus hosted liquid oceans for as long as 100 million years before its runaway greenhouse fully engaged, as some climate models suggest, then the inner edge of habitability may sit closer to the star than the theoretical runaway limit implies. If Mars supported rivers and lakes for hundreds of millions of years after its formation, as its geology strongly suggests, then the outer edge may sit farther from the star than the maximum greenhouse calculation indicates. The optimistic zone for our Sun runs from roughly 0. 75 astronomical units to roughly 1. 77 astronomical units, a band nearly twice as wide as the conservative one. Most of the headlines about newly discovered, potentially habitable worlds use the optimistic zone because it is more inclusive and produces larger numbers. Most peer-reviewed statistical estimates of the habitable planet population use the conservative zone because it rests on more defensible theoretical foundations. The choice between them changes the inferred number of habitable worlds in the galaxy by a factor of roughly 2, which sounds modest until you remember that the baseline number is already in the tens of billions. For stars other than the Sun, the habitable zone sits at different orbital distances scaled by the host star's luminosity. A dim red dwarf has a habitable zone that hugs the star at fractions of 1/10 of an astronomical unit, with planets completing their orbits in days rather than years. A hot blue-white star has a habitable zone far out at distances where orbital periods run to years or decades. The zone is always defined by the same temperature window, but the window can sit anywhere from nearly touching the star to far out in what we would otherwise think of as the cold outer reaches of system. The habitable zone is, in the most honest available framing, the necessary address without any promise about what the address contains. A planet can occupy the right orbital band and still be uninhabitable for reasons that have nothing to do with its distance from its star, and the list of those reasons is long enough to be humbling. A world without a substantial atmosphere has no mechanism to maintain surface temperatures in the liquid water range regardless of how much stellar energy it receives. A world with too thick an atmosphere can greenhouse itself into Venus-like conditions, even at distances that would otherwise be safely temperate. A tidally locked world, one that keeps the same face permanently toward its star, presents a permanently illuminated hemisphere and a permanently dark one, requiring specific atmospheric dynamics to create any habitable middle ground between the two extremes. A world without a global magnetic field is exposed to its host star's continuous outflow of charged particles, which over billions of years can strip away an atmosphere the way a slow, persistent wind erodes a sandstone cliff. A world without plate tectonics lacks the carbon cycle that acts as a planetary thermostat, regulating surface temperature across billions of years of gradual stellar brightening. A world without a large stabilizing moon may have its rotational axis wander over tens of millions of years, producing climate swings far more violent than anything Earth has experienced in its long history. Each of these conditions is independent of orbital distance, and each one can turn a habitable zone address into an uninhabitable surface. The habitable zone is the first filter in a long sequence of filters, and the catalog's named candidates are the worlds that have passed the first one without yet being tested against the rest. The galactic habitable zone adds one more layer to the address, situating the question not just within a planetary system, but within the larger structure of the galaxy itself. The Milky Way is not uniformly hospitable to long-lived planetary life, and the reasons are worth holding briefly. Near the galactic center, the density of stars is high enough that supernova events are frequent, and the radiation environment from those explosions can sterilize planetary surfaces and disrupt atmospheric chemistry on timescales shorter than the hundreds of millions of years that complex life seems to require. Far from the galactic center, the fraction of heavier elements in the interstellar gas drops below the level needed to form rocky planets in significant numbers, because those heavier elements were themselves forged in earlier generations of stars and distributed by their deaths. The intersection of these two constraints defines a ring-shaped region of the galaxy, roughly 7 to 9 kiloparsecs from the galactic center, within which the conditions for long-lived rocky planet formation and biological persistence are most favorable. The Sun sits at approximately 8 kiloparsecs from the galactic center, comfortably within this ring, which is either another reassuring calibration or another reminder that the definition was built around the one inhabited world we know. Estimates place roughly 20 to 30% of all stars in the Milky Way within this galactic habitable zone, a fraction that further modifies the headline numbers when the full conditional chain is assembled. The habitable zone around a star is the local address. The galactic habitable zone is the neighborhood, and not all neighborhoods in the galaxy are equally safe for the long, slow project of biological complexity. What all of this means in practice is that the confirmed habitable zone worlds in the catalog are worlds that have passed the simplest and most tractable of the habitability tests, the temperature window, without yet being fully evaluated against a longer and more demanding list of further requirements. A confirmed habitable zone planet is a real and important detection, the kind of result that would have seemed extraordinary just 30 years ago when the first exoplanet around a sun-like star had not yet been found. It is also only the beginning of the question, because the temperature window is the part of habitability that current instruments can measure, and the remaining conditions are the parts that require either more powerful instruments or entirely different observational approaches. The named worlds in the catalog are the ones where the first question has been answered well enough to make the second question worth asking in earnest. Whether they have atmospheres, whether those atmospheres are the right kind, whether the host stars are calm enough to have preserved them across billions of years, whether the planetary interiors have sustained the heat and chemistry that life requires, all of that remains open for most of the catalog's entries. The habitable zone is the address on the envelope, and what is inside the envelope is what the next decade of observations is being built to read. The first name on the list is already waiting, and it is the one that opened the door to all the others, the planet that turned the question from a statistical inference into a specific place with a name. The conservative count, as it turns out, is not the ceiling of the question, but rather its floor. Everything examined so far has assumed that habitability means surface liquid water under an open sky, a rocky world warmed by its star to temperatures where oceans can form and persist across geological time. That assumption is built entirely from Earth, the one inhabited world we have as a reference, and it may be the most consequential bias in the entire field. When you step back from that assumption and ask where liquid water actually exists in the solar system right now, the answer is not primarily on Earth's surface. The answer is buried beneath the ice of moons that orbit far beyond any conventional habitable zone, in places that receive so little starlight that no surface ocean could survive for a single winter. The total volume of liquid water in those hidden places exceeds the liquid water on Earth's surface by a factor estimated at more than 30. That single fact quietly dismantles the assumption that the habitable zone is where habitability lives, and it opens the door to a much larger and stranger catalog than the one the transit surveys have built. Europa is the first and most studied example of what lies behind that door. It is the smallest of Jupiter's 4 large Galilean moons, a body roughly the size of Earth's moon, and it carries beneath its cracked and striated ice shell a global ocean of liquid salt water that has likely persisted for billions of years. The ice shell is estimated to be somewhere between 10 and 30 kilometers thick, a frozen ceiling over an ocean that may be 100 kilometers deep in places. The heat that keeps that ocean liquid does not come from the sun, which delivers almost nothing useful at Jupiter's distance. It comes from tidal friction, the constant flexing of Europa's interior as Jupiter's immense gravity stretches and compresses the moon on every orbit, generating heat the way a repeatedly bent wire generates heat in your fingers. Beneath the ice, where the ocean meets the rocky seafloor, hydrothermal vents may exist, producing the kind of chemical disequilibrium that powers entire ecosystems around Earth's mid-ocean ridges without any sunlight at all. Europa is, by every physical measure we can apply from a distance, a world where the conditions for life as we understand it could plausibly exist, and it orbits a planet that sits more than 5 astronomical units from the sun, well outside every version of the conservative habitable zone ever drawn. Enceladus extends the argument further and adds a detail that makes it uniquely compelling among all the solar system's ocean worlds. This small moon of Saturn, barely 500 kilometers across, is actively leaking its interior ocean into space through a series of cryovolcanic plumes erupting from fractures near its south pole. The Cassini spacecraft spent years orbiting Saturn and made multiple passes directly through those plumes, sampling their contents at close range and returning a chemical inventory that reads like a checklist of prerequisites. The plumes contain water, salts, silica particles that indicate hot water in contact with rock, simple organic molecules, and molecular hydrogen, the last of which is a known energy source for microbial life around Earth's hydrothermal vents. Enceladus is in the remarkable position of advertising its subsurface chemistry to any spacecraft that happens to pass nearby, which means that detecting potential biosignatures there requires no drilling, no landing, and no complex surface operations. A future mission need only fly through the plumes with the right instruments to sample whatever the ocean contains. Whether anything is alive in that ocean is entirely unknown, but the ocean itself is real, the chemistry is suggestive, and the access is extraordinary by any standard of planetary exploration. Ganymede, Callisto, Titan, Triton, Pluto, and possibly several of the larger dwarf planets in the Kuiper Belt add further entries to the subsurface ocean inventory, each one a world where liquid water persists in the dark beneath a frozen exterior. Titan carries the additional distinction of having surface lakes and rivers of liquid methane and ethane alongside its deep subsurface water ocean, making it the only world beyond Earth known to have stable liquids pooling on its surface, even if those liquids are not water. The picture that emerges from the solar system alone is that liquid water is not rare in the galaxy, and it is not confined to the narrow band of orbital distances where starlight can warm a rocky surface. It is hidden, it is sealed, it is dark, and it is abundant. Extended to the galaxy as a whole, this changes the population picture in ways that the conservative habitable zone count cannot capture. A rocky moon in tidal contact with a giant planet can host a long-lived subsurface ocean at almost any orbital distance from its host star. A world ejected from its system into interstellar space can maintain subsurface liquid water through its own internal heat alone, drifting through the dark with no star to warm it, potentially for billions of years. The Hycean planet is the second major expansion of the habitability concept, and it represents a class of world that may be far more common than rocky Earth analogs, while being far more accessible to atmospheric characterization with current instruments. The name combines hydrogen and ocean, and it describes a sub-Neptune-sized world, somewhere between 1 and 3 Earth radii, carrying a thick hydrogen-rich atmosphere over a global liquid water ocean beneath. The hydrogen envelope acts as a powerful insulating layer, trapping heat in a way that allows the ocean beneath to remain liquid even when the planet's equilibrium temperature in the absence of any atmosphere would be well below freezing. This means that Hycean worlds could maintain habitable conditions at orbital distances significantly farther from their host stars than the conservative habitable zone would predict, effectively extending the outer boundary of where life might exist by a meaningful margin. The class is hypothesized rather than confirmed, meaning no world has yet been definitively established as a Hycean planet. But the physical reasoning behind the concept is sound, and the observational evidence from at least one candidate is beginning to accumulate in ways that the field is taking seriously. If the class is real and common, it could substantially increase the number of potentially habitable worlds in the galaxy beyond what the rocky planet count alone suggests. Tidal locking, long treated as a death sentence for habitability around small red dwarf stars, has been partially rehabilitated by more careful climate modeling over the past decade. A tidally locked planet keeps one hemisphere permanently facing its star and the other permanently turned away, a configuration that initially seems to guarantee a scorched day side and a frozen night side with no comfortable middle ground for life. The newer modeling tells a more nuanced story. A planet with even a modest atmosphere will transport heat from its illuminated hemisphere to its dark one through atmospheric circulation, driven by the temperature difference between the two sides. The result is a ring of moderate temperature at the terminator, the permanent twilight boundary between day and night, where conditions might remain within the range that life on Earth would tolerate. The terminator on such a world would be a place of perpetual dim reddish light, the host star hanging motionless on the horizon for billions of years, neither rising nor setting. while the planet's weather systems circulate heat around the boundary between warmth and cold. Whether life could actually thrive in such a zone remains an open question, but the modeling suggests that tidal locking alone is not sufficient to rule a world uninhabitable, which matters considerably given that most of the habitable zone planets around the galaxy's most common stars are almost certainly tidally locked. Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, offers the most direct evidence that subglacial habitability is not merely theoretical. The lake has been sealed from the surface for an estimated 15 to 25 million years, receiving no sunlight, no surface weather, and no input from the atmosphere above the ice. Despite this, the microbial community living in its cold, dark water draws on chemical energy from the surrounding rock and the slow dissolution of minerals from the ice ceiling above, maintaining a functioning ecosystem without any photosynthesis whatsoever. Extended to the planetary scale, this means that a world entirely covered in ice, sitting well outside any version of the habitable zone, could still host habitable conditions at the rock-ice interface, where geothermal heat, hydrothermal chemistry, and mineral dissolution provide the energy and nutrients that life requires. The surface of such a world would be indistinguishable from a frozen, lifeless rock to any distant observer. The habitability would be entirely invisible from the outside, which raises the uncomfortable question of how many worlds in the galaxy we have already dismissed as frozen and dead that might be quietly alive in the dark beneath their ice. The rogue planet population adds yet another dimension to the count, one that is only beginning to be quantified by microlensing surveys. The Milky Way contains an estimated several hundred billion planets that orbit no star at all, worlds that were either born in the collapse of gas clouds too small to ignite as stars, or were ejected from their original systems during the chaotic gravitational interactions of early planetary formation. Microlensing data suggests these rogue planets may outnumber stars in the galaxy by a factor of several, making them among the most common planetary bodies in existence by sheer number. Most of them are probably small and cold all the way through, with no internal heat source sufficient to maintain liquid water anywhere in their interiors. But the larger ones, the rogue super-Earths and rogue Neptune-mass worlds, can retain enough heat from primordial radioactive decay to keep subsurface oceans liquid for billions of years without any external energy source. A rogue planet with a thick hydrogen atmosphere, insulating its interior against the cold of interstellar space, could in principle maintain a subsurface ocean almost indefinitely, drifting through the dark between the stars with no address in any habitable zone catalog, invisible to every transit survey ever conducted, and possibly alive in ways we have no current means to detect. Exomoons complete the picture by pointing to a category of habitable worlds that the galaxy almost certainly contains in large numbers, but that current instruments cannot yet confirm. The solar system's own inventory makes the case plainly enough. Europa, Enceladus, Titan, possibly Ganymede, and Callisto represent 5 separate potentially habitable environments around 2 giant planets, none of which is in the habitable zone of the Sun by the surface water definition. By analogy, the galaxy should contain a vast population of large moons in stable orbit around giant planets, themselves orbiting within or near the habitable zones of their host stars, each one a potential Europa or Enceladus scaled up to planetary mass. The detection of exomoons sits at the very edge of current observational capability, and no confirmed exomoon has yet been added to the catalog despite several tantalizing candidates. The first confirmed habitable exomoon, when it arrives, will substantially shift the population count, because the number of giant planets in habitable zones is itself large, and each giant planet can in principle host multiple large moons in stable orbits. The exomoon population is almost certainly real, almost certainly large, and almost entirely invisible to current instruments. Taken together, these 6 expansions of the habitability concept, subsurface oceans, Hycean worlds, tidally locked terminator zones, subglacial environments, rogue planets, and exomoons, transform the question from a narrow search for rocky worlds in a specific temperature band into something much broader and stranger. The galaxy is not divided into a small ring of habitable space around each star and a vast, uninhabitable darkness beyond. It is more like a slow scattering of pockets, each one small, most of them dark, most of them sealed beneath ice or wrapped in hydrogen or drifting alone through interstellar space. Each one a place where water is liquid and chemistry is possible and the conditions for life as we understand it could in principle be met. The conservative count of tens of billions of habitable worlds is the count of places that pass the simplest and most tractable of the habitability tests, the surface temperature window around a host star. The broader count, the one that includes all the ways the galaxy has learned to keep water liquid, is larger by orders of magnitude that resist easy expression. The conservative number is where the catalog begins, and the named worlds in that catalog are the places where the question becomes specific enough to hold in the mind as something more than an estimate. Each of those names is a door, and behind each door is a world with its own particular history and its own particular chances, waiting for the instruments that are already being built to finally look closely enough to read what is there. The first name in the catalog is the one that made the question into a question about specific places rather than abstract statistics. Before 2011, the existence of habitable zone worlds around sun-like stars was a statistical inference built on incomplete data and reasonable hope. The confirmation of Kepler 22b changed the texture of that inference into something you could point at directly. It sits in the constellation Cygnus, roughly 620 light-years from Earth, orbiting a G-type star that is slightly cooler, slightly smaller, and slightly dimmer than our own Sun. The host star's surface temperature runs about 300 degrees below the Sun's, and its luminosity reaches approximately 79% of what our star produces on any given day. The planet completes one full orbit every 290 Earth days, tracing a path at about 0.85 astronomical units from its host, closer in than Earth sits relative to the Sun. Because the star is dimmer, that closer distance still places the planet comfortably inside the conservative habitable zone near its inner edge. Without any atmospheric warming, the equilibrium temperature sits around 260 Kelvin, roughly negative 12 degrees Celsius, cold enough to freeze an unprotected surface solid. Add an Earth-like atmosphere and reasonable greenhouse warming, and the surface temperature climbs to something close to Earth's own average of around 15 degrees Celsius. The Earth Similarity Index for Kepler 22b sits at approximately 0.84, high enough to make it one of the most discussed entries in the entire catalog. The most important uncertainty about Kepler 22b is also the one that most popular coverage tends to quietly sidestep when describing the planet. Its radius measures approximately 2.4 times Earth's, placing it in a transitional range between rocky super-Earths and volatile-rich mini-Neptunes, where composition cannot be inferred from size alone. Without a direct mass measurement, the question of what Kepler 22b is actually made of remains genuinely open in a way that matters enormously for habitability. If the planet is rocky, it carries significantly higher surface gravity than Earth and likely a thicker, denser atmosphere pressing down on whatever surface exists beneath. If it is volatile-rich, the most popular conjecture among researchers who have studied it carefully, it is probably an ocean world, a planet covered from pole to pole in a global ocean potentially hundreds of kilometers deep. If it is hydrogen-rich, it is a mini-Neptune with no solid surface at all, just a thick gaseous envelope wrapping a compressed interior far below. The ocean world interpretation has the most support by elimination, because the density required for a purely rocky composition at that radius would be unusually high by the standards of the known catalog. A planet covered entirely in deep water beneath a thick cloudy atmosphere would have no continents, no shorelines, no exposed rock anywhere on its surface. It would be a world of unbroken ocean stretching from horizon to horizon, indifferent to whether anything has ever swum through it. The enthusiasm that followed the 2011 confirmation announcement produced some of the most quoted and most frequently misunderstood numbers in the modern history of exoplanet research. Individual researchers, speaking in informal interviews rather than in peer-reviewed papers, placed the odds of life on Kepler 22b at figures as high as 95 to 99%, numbers that circulated widely and have never quite left the popular conversation around the planet. Those figures were not the field's consensus and were never intended to function as formal probability estimates in any rigorous sense. They expressed something real, which was the genuine surprise that habitable zone worlds around sun-like stars turned out to be so much more common than the field's pre-Kepler expectations had predicted. The discovery arrived earlier and more easily than many researchers had quietly assumed it would, and the enthusiasm that followed was proportional to that surprise rather than to any specific calculation about biological probability. The proper framing 15 years later is considerably more careful about what the detection actually established and what it left entirely open. Kepler 22b sits in the habitable zone of a sun-like star, and that fact is confirmed and real and important. Whether it has an atmosphere, whether that atmosphere is the right kind, whether the host star has been calm enough to preserve it across billions of years, whether anything exists in whatever ocean the planet may carry, all of that remains completely unknown. The discovery was the proof of concept, not the answer. Kepler 452b arrived 4 years after Kepler 22b and drew a similar wave of attention for reasons that were in some ways even more compelling than the first discovery. Its host star, designated Kepler 452, is a G-type star with a surface temperature within 20 degrees of the Sun's, making it one of the closest stellar analogs to our own Sun, yet found to host a confirmed habitable zone candidate. The planet orbits at approximately 1.05 astronomical units, almost exactly Earth's distance from the Sun, and completes one circuit every 385 Earth days, within 5% of an Earth year. Its radius measures about 1.6 Earth radii, larger than Earth, but small enough to sit within the range where a rocky composition remains physically plausible. The estimated mass of approximately 5 Earth masses would give the planet a surface gravity roughly twice Earth's, a detail that matters for atmospheric retention and for the physical experience of anything that might live there. The detail that most captured public attention, however, was the age of the host star, estimated at approximately 6 billion years, more than 1 billion years older than our own Sun. On the only timescale of biological complexity we have as a reference, 1 billion years is the difference between a planet of single-celled microbes and a planet of organisms capable of looking back at the sky and wondering what else is out there. If life arose on Kepler 452b at any plausible early date in its history, it has had more time to evolve than life on Earth has yet had available to it. The older cousin framing that attached itself to Kepler 452b in press coverage carried a genuine insight alongside the inevitable simplification that comes with any catchy label. An older sun-like star in a habitable zone configuration does represent a meaningful difference from Earth's situation because it means more time for whatever processes biology requires to run their course. The complication is that older also means a star that has been slowly brightening across its main sequence lifetime, and Kepler 452b sits near the inner edge of its host star's habitable zone in a way that makes that brightening directly relevant. Main sequence stars increase in luminosity by roughly 10% per billion years as hydrogen fusion gradually alters the core's composition and structure. The inner edge of the habitable zone moves outward as the star brightens, and Kepler 452b, fixed in its orbit, may already be in the early stages of the kind of runaway greenhouse that Venus is believed to have undergone in our own solar system's history. Some climate modeling work suggests the planet may have already crossed that threshold, while other work suggests it remains habitable for some hundreds of millions of years longer, and the transition itself is far too slow for any current observation to capture directly. A second complication arrived in 2018 when a follow-up statistical analysis suggested the original transit detection might be a false positive caused by stellar variability rather than a real planetary crossing. The planet status is currently listed as confirmed in the mainstream catalog, but the confidence behind that listing is weaker than the original press release implied, and the script should hold that honestly rather than papering over the uncertainty with enthusiasm. Kepler 186f and Kepler 1649c represent two quieter, but in some ways more precisely defined entries in the catalog, each one significant for a specific technical reason that the headline worlds sometimes overshadow. Kepler 186f, announced in 2014, was the first planet within 10% of Earth's own radius ever found in the habitable zone of any star, a milestone that matters because radius is the measurement most directly connected to whether a world is likely rocky rather than gaseous. Its host is a small M-dwarf called Kepler 186, sitting about 580 light-years away, and the planet orbits with a period of 129 Earth days at a distance that places it inside the habitable zone given the star's dim output. The equilibrium temperature without atmospheric warming sits around 180 Kelvin, approximately negative 93 degrees Celsius, cold enough that a thick atmosphere would be essential for any surface liquid water to persist. Kepler 1649c, confirmed in 2020 from a reanalysis of archival Kepler data, carries a radius of approximately 1.06 Earth radii and receives about 75% of the stellar flux that Earth receives from the Sun, making its energy environment one of the closest matches to Earth's yet found among confirmed candidates. Its orbital period of roughly 19.5 days is short by Earth standards, but entirely typical for a planet in the habitable zone of a small cool star. Both worlds carry the standard M-dwarf caveats about tidal locking, host star flare activity, and unknown atmospheric status, and both remain among the highest-ranked entries on Earth Similarity Index calculations across the entire confirmed catalog. The nearest known potentially habitable world sits at a distance that is practically intimate by the standards of everything else in the catalog, which is part of what makes Proxima Centauri be simultaneously the most exciting and the most uncertain entry on the entire list. At 4.24 light-years, it orbits the closest star to the solar system, a small M-dwarf called Proxima Centauri that is the faintest and least massive of the three stars making up the Alpha Centauri system. The planet was confirmed in late 2016 through a careful radial velocity campaign that detected the host star's small periodic wobble, repeating every 11.2 Earth days and indicating a planet of at least 1.07 Earth masses orbiting at approximately 0.049 astronomical units. That orbital distance is closer to Proxima than Mercury sits to the Sun by a factor of 8. But because the host star is roughly 17,000 times less luminous than the Sun, the planet receives approximately the same energy budget that Earth receives from our own star. The equilibrium temperature without atmospheric warming sits around 234 Kelvin, roughly negative 40 degrees Celsius, and with a thick enough atmosphere the surface could warm into the range where liquid water might persist. The standard statistical correction for unknown orbital inclination pushes the expected true mass to somewhere around 1.3 to 1.4 Earth masses, consistent with a rocky world rather than a gaseous one, though the composition cannot be confirmed without a radius measurement that current methods cannot yet provide. The complications that surround Proxima b are substantial enough that the planet occupies a peculiar position in the catalog, simultaneously the most accessible candidate for future direct characterization and the one where the gap between address and actual habitability may be largest. Tidal locking is almost certainly present given the planet's orbital distance and the system's age of more than 4 billion years, meaning one hemisphere faces the star permanently while the other never receives direct illumination. The day side without atmospheric heat transport would be warm enough to be hostile to most surface biology, while the night side would be cold enough to freeze any volatile that migrated there from the lit hemisphere. Whether Proxima b has enough atmosphere to bridge that temperature gap through circulation is the central open question, and the host star's behavior makes it a genuinely difficult one. Proxima Centauri is a flare-active M-dwarf that produces frequent ultraviolet and X-ray outbursts, with the most intense events delivering radiation doses at the planet's orbital distance that are hundreds to thousands of times more energetic than the strongest solar events Earth experiences. Repeated across billions of years of the system's history, the kind of stellar activity is capable of stripping an unprotected atmosphere away over geological time, leaving the planet as bare exposed rock with no buffer between its surface and the full flare environment. Some modeling work suggests the atmosphere has already been lost entirely, while more optimistic models argue that a strong enough initial volatile inventory combined with a robust magnetic field could have preserved habitable conditions in the Terminator Twilight Zone despite the ongoing bombardment. The extremely large telescopes currently under construction should be capable of directly imaging Proxima b and obtaining atmospheric spectra within the next 10 to 15 years, which means the question of whether it has an atmosphere at all is one of the nearest term resolvable uncertainties in the entire catalog. The TRAPPIST. One system represents the catalog's most remarkable single entry, a configuration so architecturally unusual and so scientifically rich that it has commanded more observational attention than any other habitable zone system discovered in the past decade. The host star sits 39.6 light-years away in Aquarius, an M8V ultracooled dwarf with a mass of approximately 0.089 solar masses, a radius slightly larger than Jupiter's, and a surface temperature of around 2,500 Kelvin, the color of a dim red ember barely holding its fusion above the threshold that separates true stars from brown dwarfs. Around this faint and ancient star, which has been burning hydrogen slowly for approximately 7.6 billion years and will continue doing so for trillions more, 7 confirmed Earth-sized rocky planets orbit in a tightly packed resonant chain, where consecutive orbital periods form near-integer ratios that have held the system gravitationally stable across its entire long history. The orbital periods run from 5 days for the innermost planet to 19 days for the outermost, and the entire system fits within an orbital radius smaller than Mercury's path around the Sun. From the surface of any one of these worlds, the neighboring planets would appear as visible disks in the sky, close enough at their nearest approaches to show surface features to an unaided eye, a proximity that has no analog anywhere in our own solar system. The 3 habitable zone planets, designated E, F, and G, have drawn the most sustained research attention, with TRAPPIST, 1E carrying an Earth similarity index of approximately 0.95, the highest of any confirmed exoplanet in the entire catalog, and a mass of about 0.69 Earth masses on a radius of roughly 0.92 Earth radii that makes it the closest physical match to Earth yet found among confirmed worlds. The James Webb Space Telescope's first results from the TRAPPIST-1 system arrived with a sobriety that tempered some of the system's earlier optimism, and the implications for the habitable zone planets remain one of the most actively watched questions in current exoplanet research. Observations of the 2 innermost planets, TRAPPIST-1b and TRAPPIST-1c, measured their dayside brightness temperatures in thermal infrared and found them consistent with bare rocky surfaces in direct equilibrium with the stellar flux, showing no evidence of the atmospheric heat redistribution that a substantial gaseous envelope would produce. The most direct interpretation is that both inner planets are naked rock, their atmospheres stripped away by billions of years of exposure to the host star's flare activity and stellar wind, baked on their day sides and frozen on their night sides with nothing to soften the difference. Whether the habitable zone planets E, F, and G have fared better is the question that the next round of JWST observations is specifically designed to address, and the early results from the inner planets are not encouraging as a baseline expectation. The system's 7.6 billion year history is long enough for significant atmospheric erosion even at the outer orbital distances, and the host star, while comparatively quiet for an ultracooled dwarf, has still had billions of years to work on whatever atmospheres those worlds began with. Whatever the next observations show, TRAPPIST-1 will remain the strongest available test of M-dwarf habitability at the population level, the place where the question of whether the galaxy's most common stars can host living worlds is being answered one planet at a time. And the world that sits waiting most patiently for the answer is K2-18b, 124 light-years away, with something faint and suggestive already written in its sky. The number that organizes everything else in this part of the question has a name borrowed from the Greek alphabet. Eta Earth, written with the symbol that looks like a stylized N, is defined precisely as the average number of Earth-sized planets in the habitable zone per Sun-like star. It is the central statistical quantity of modern habitability research, the single figure that connects the named worlds of the catalog to the population-level question of how full the galaxy actually is. Current best estimates from multiple independent research teams cluster the value somewhere between roughly 0, 3, and 0, 8, a range that has proven surprisingly stable across different methodological approaches and different datasets. The most carefully constructed current estimate, drawn from a NASA analysis published in 2021 using the complete Kepler mission dataset, places Eta Earth at approximately 0, 5 for Sun-like stars specifically. A conservative reading of the available evidence pushes the number down towards 0, 1, meaning roughly 1 in 10 Sun-like stars hosts a habitable zone Earth analog. The optimistic reading pushes it towards 0, 8, meaning nearly 4 out of every 5 Sun-like stars carry such a planet somewhere in its system. The honest current position is that the true value lives somewhere within that full span, and no measurement yet made has been precise enough to narrow it further. The uncertainty is not a failure of the field, but a reflection of how genuinely difficult it is to correct for the detection biases that the transit method introduces into the catalog. What the range tells us, even at its most conservative end, is that habitable zone Earth-sized planets are not rare exceptions scattered thinly through an otherwise empty galaxy. Multiplying Eta Earth by the number of stars in the Milky Way is where the headline figure comes from, and the arithmetic is worth following carefully enough to trust the result. The Milky Way contains approximately 400 billion stars of all types, a number that itself carries significant uncertainty but is well established within a factor of 2. Of those stars, roughly 10% qualify as G-type Sun-like stars by the strictest definition, the kind of quiet, stable, middle-aged hydrogen burners that our own Sun represents. That strict fraction yields approximately 40 billion Sun-like stars as the baseline population. Apply even the conservative end of the Eta Earth range to that baseline, and the result is several billion Earth-sized habitable zone planets in the Milky Way around the Sun-like stars alone. Apply the midpoint estimate of 0, 5, and the figure climbs to roughly 20 billion, which is a number most often cited in careful popular coverage of the question. Broaden the definition of Sun-like to include K-type stars, slightly smaller and cooler, but stable and long-lived, and the quietest M-dwarfs, and the eligible stellar population grows substantially beyond that 10% figure. The broader definition produces headline estimates in the range of 40 billion or more potentially habitable Earth-sized worlds in the Milky Way, which is the figure that has entered the public conversation most durably over the past decade. The honest range, holding both ends of the uncertainty simultaneously, runs from perhaps 2 billion at the most pessimistic to perhaps 100 billion at the most optimistic, depending on which stars are included and which Eta Earth value is applied. The order of magnitude is settled in a way the precise value is not, and that order of magnitude is large enough to constitute an answer to the question of whether the galaxy is full of habitable places. Extending the count beyond the Milky Way requires one more multiplication that pushes the numbers into territory where language begins to fail as a measurement tool. The observable universe contains somewhere between 200 billion and 2 trillion galaxies, a range that was substantially revised downward by James Webb Space Telescope deep field observations that found fewer faint distant galaxies than earlier estimates had assumed. The Milky Way is a relatively large and well-populated galaxy by the standards of the universe as a whole, meaning the average per galaxy habitable planet count is probably somewhat lower than our own galaxy's figure. A rough but defensible estimate places the number of Earth-similar habitable zone worlds in the observable universe at somewhere between 10 to the 18th power and 10 to the 22nd power, which translates into the English words 1 quintillion and 10 sextillion respectively. Those words function as placeholders rather than quantities in any felt sense, the way the word infinity functions as a placeholder for something the mind cannot actually hold. What they mean in practice is that the universe has been making potentially habitable worlds at a rate and in a volume that renders the question of whether any of them are inhabited into something other than a question about scarcity. The scarcity, if it exists, is not in the habitable worlds themselves, but in whatever chain of events converts a habitable world into an inhabited one. That chain is where the question gets genuinely hard, and where the honest answer requires acknowledging how little we currently know. The Drake equation is the formal structure that organizes the multiplicative reasoning from habitable worlds to communicating civilizations, and it is worth holding in the way it was actually intended, as a framework for mapping ignorance rather than as a calculation that produces a reliable answer. Frank Drake wrote the equation in 1961 to structure the first scientific conference on the search for extraterrestrial intelligence, and its 7 factors run from the rate of star formation in the galaxy through the fraction of stars with planets, the number of habitable planets per such star, the fraction where life arises, the fraction where intelligence arises, the fraction developing communicative technology, and finally the average lifetime of such civilizations. The first 3 factors are the ones that modern exoplanet science has substantially addressed, and the progress on them over the past 3 decades has been one of the genuine achievements of the era. The rate of star formation in the Milky Way is well measured and well understood within the context of galactic evolution. The fraction of stars with planets of some kind is now known to be essentially 1, meaning virtually every star in the galaxy hosts at least one planetary body of some description. The habitable planet fraction, eta Earth, has been bracketed between 1 and 8 by the Kepler and TESS missions, a range that was completely unconstrained as recently as the early 2000s. The first half of the equation has been transformed from speculation into observational science, which is a genuine and underappreciated revolution in how precisely the question can be framed. The second half of the Drake equation is where the honest acknowledgement of ignorance becomes the dominant note, and where the range of scientifically defensible answers spans many orders of magnitude simultaneously. The fraction of habitable worlds where life actually arises, the abiogenesis probability, is the factor that most directly determines whether the galaxy is biologically rich or biologically sparse, and it is entirely unconstrained by current evidence. We have one example of a planet where life arose, and that example tells us only that the probability is greater than 0, which is not a useful lower bound when the question is whether it is 1 in a billion or 1 in 1. The fraction of inhabited worlds where intelligence emerges is similarly unconstrained, resting on a single data point whose typicality cannot be evaluated. The fraction of intelligent civilizations that develop communicative technology, the fraction that then actually broadcast detectable signals, and the average lifetime of such civilizations before they go silent or disappear entirely, all remain unknown by amounts that dwarf the uncertainties in the first half of the equation. The product of the second half's factors could be as large as 1, meaning nearly every habitable world eventually produces a communicating civilization, or as small as 1 in a trillion, meaning Earth is the only such civilization in the observable universe. Both values are consistent with current evidence, which is itself one of the most important and least comfortable facts in modern science. The Copernican position and the rare Earth position represent the 2 poles of the debate about what the second half of the Drake equation actually contains, and both deserve to be held as genuinely open rather than as one obvious answer and one fringe view. The Copernican position holds that Earth should be treated as roughly typical of inhabited worlds rather than as an extraordinary exception, and that the conditional probabilities of life, intelligence, and technology are large enough that the galaxy should contain many other civilizations if habitable worlds are as common as the first half of the equation suggests. The rare Earth position holds that the architectural requirements for long-lived, complex life are far narrower than the habitable zone definition implies, and that the conjunction of all the necessary conditions, the right star type, the right galactic location, the magnetic field, the plate tectonics, the stabilizing moon, the long-lived atmosphere, the protective outer planets, the stable rotational axis, the absence of catastrophic impacts across billions of years, is rare enough that Earth, like inhabited worlds, may be extraordinarily sparse. Each individual condition on the rare Earth list is plausible and physically motivated. The question is whether the conjunction of all of them simultaneously is common enough to populate the galaxy with many inhabited worlds or rare enough to leave it nearly empty. We have one example, and one example cannot distinguish between these two positions with any statistical confidence whatsoever. The honest position is that both views are scientifically respectable, that neither has been falsified by available evidence, and that the instruments needed to begin distinguishing between them are either already operating or currently under construction. The eukaryotic transition is the biological event most often cited as the candidate bottleneck step in the conditional probability chain, and its apparent singularity in Earth's history gives the rare Earth position one of its most compelling specific arguments. Life on Earth arose within a few 100 million years of the planet becoming habitable, a speed that suggests abiogenesis may not be the bottleneck. But the transition from simple prokaryotic cells to the complex eukaryotic cells that carry a nucleus and organelles and the machinery for sexual reproduction took roughly 2 billion additional years and appears, from the available fossil and genetic evidence, to have occurred exactly once in Earth's entire history. Every complex organism alive today, every plant, every animal, every fungus, every protist descend from a single ancestral eukaryotic cell that emerged from a merger between two prokaryotic lineages in circumstances that have never been replicated in 4 billion subsequent years of microbial evolution. Whether that merger was a one-in-a-universe accident or a predictable outcome that simply requires the right conditions and enough time is one of the deepest open questions in biology. If it was genuinely improbable, then planets covered in microbial life may be common, while planets with anything more complex are extraordinarily rare. If it was merely slow, then complexity may be a universal feature of sufficiently old biospheres, and the galaxy may be rich with organisms that have had billions of years to develop beyond the prokaryotic stage. The question cannot be answered from a sample of one, which is the fundamental epistemological problem that the entire second half of the Drake equation faces. The Great Filter is the conceptual framework that organizes the implications of the second half of the equation into its most consequential form, and it arrives in this part of the catalog with a weight that deserves to be acknowledged directly rather than softened into abstraction. The idea is that somewhere along the chain from a habitable world to a communicating technological civilization, there's at least one step that is fantastically improbable, a filter narrow enough to explain why the galaxy appears empty despite the abundance of habitable worlds. The filter's location relative to our current position is the question that carries the most existential weight. If the filter is behind us, if the hard step was abiogenesis or the eukaryotic transition or the emergence of intelligence, then we have already passed through the bottleneck and the road ahead may be relatively open. If the filter is ahead of us, if the hard step is the long-term survival of technological civilizations in the face of the risks they generate for themselves, then we may not yet have reached the narrowest gate in the sequence. The arguments for a behind-us filter rest on the apparent singularity of certain biological transitions in Earth's history and on the relative speed with which life and intelligence emerged once the planet became habitable. The arguments for an ahead-of-us filter rest on the difficulty of sustaining complex technological civilization across the timescales that interstellar detectability requires. Both arguments are coherent, and neither has been falsified. which means the filter's location remains genuinely unknown and the implications of each possibility remain genuinely different in ways that matter beyond the scope of this catalog. Several decades of radio searches, optical laser surveys, and waste heat infrared observations have produced no confirmed evidence of any technological civilization anywhere in the galaxy. And that silence is a real and information-carrying fact rather than simply an absence worth noting in passing. The searches have not been comprehensive in any sense that would make the silence conclusive. They have covered a small fraction of the sky to a limited depth at a limited range of frequencies with instruments that would not detect our own civilization's radio leakage from more than a few light years away. The silence is consistent with a galaxy full of civilizations that are simply too distant, too quiet, or too different in their communication methods for current searches to find. It is equally consistent with a galaxy where technological civilizations are rare enough that the nearest one, if it exists, is thousands or tens of thousands of light years away. It is consistent with civilizations that deliberately avoid broadcasting or that have moved beyond radio communication into methods we have not yet thought to search for, or that exist on timescales so different from ours that our century of listening has not overlapped with any of their transmission windows. The silence does not tell us which of these explanations is correct, and the honest acknowledgement of that is more useful than treating the silence as evidence for any particular conclusion. What it tells us with certainty is that the galaxy contains no civilization currently broadcasting detectable signals in ways that our existing instruments can receive, which is a much narrower statement than the one that popular coverage sometimes implies. The gap between the enormous habitable count and the single confirmed inhabited world is the honest resting place for this part of the question, and it is worth sitting with that gap directly rather than rushing past it toward either optimism or pessimism. The galaxy almost certainly contains somewhere between several billion and several hundred billion worlds where the conditions for liquid water exist and where the architecture of star and planet is compatible with biological persistence across geological time. That number is real. It is well supported by current observational evidence, and it represents one of the most significant empirical achievements of the past 3 decades of astronomy. The number of inhabited worlds beyond Earth is currently 0 by confirmed observation, which is a different kind of real fact that sits alongside the first without canceling it. The conditional probabilities that connect those two numbers, the chain from habitable to inhabited to intelligent to communicative, remain unknown by amounts that span many orders of magnitude and that current instruments cannot resolve. The next 2 decades of observation, from James Webb through the extremely large telescopes and toward the Habitable Worlds Observatory, are specifically designed to begin closing that gap by searching for biosignatures in the atmospheres of the nearest and most accessible habitable zone candidates. The first confirmed biosignature on any exoplanet, if it comes, will be the moment the second number changes from 1 to something larger. And everything that follows from that change is a question the catalog has been quietly building towards since the night Kepler 22b first made the question into a question about specific named places rather than abstract statistical inference. The instruments that will finally begin to answer the second half of the question are either already operating or nearly ready. James Webb has been returning atmospheric data since mid-2022, and each new observation refines the picture further. The TRAPPIST-1 inner planets showed bare rock where thick atmospheres have been hoped for. K2-18b showed methane and carbon dioxide in a configuration consistent with a global ocean beneath hydrogen skies. The next several years of Webb observations will add atmospheric characterizations to candidates that currently exist only as orbital parameters in the catalog. By the late 2020s, the field's expectations for which kinds of worlds retain atmospheres will be substantially sharper than they are tonight. The Roman Space Telescope, scheduled for launch in the late 2020s, will conduct a wide-area microlensing survey expected to reveal thousands of new worlds. Cold planets at wide separations, free-floating rogues, worlds that the transit method cannot reach, will finally become countable rather than merely estimated. The rogue planet population, currently bracketed only roughly from existing microlensing data, will be characterized in far greater detail once Roman is operational. The eta-Earth value, still spanning a factor of 8 between its conservative and optimistic bounds, may narrow considerably once Roman statistics are assembled. 3 extremely large ground-based telescopes are being built simultaneously, each one a different engineering answer to the same scientific ambition. The extremely large telescope in Chile will carry a primary mirror 39 meters across, the largest optical telescope ever constructed by a significant margin. The giant Magellan telescope, also in Chile, arranges 7 mirrors of 8, 4 meters each into a single optical system of equivalent power. The 30-meter telescope in Hawaii carries a primary mirror assembled from hundreds of hexagonal segments into a 30-meter collecting surface. All 3 are expected to reach scientific operation somewhere between the late 2020s and the early 2030s, depending on construction timelines. Each will be capable of directly imaging planets around the nearest stars and reading their atmospheric compositions through high-resolution spectroscopy. If Alpha Centauri A or B hosts an Earth analog planet, these telescopes will very likely detect it within their first years of operation. If Proxima B has retained even a thin remnant atmosphere, the spectroscopic signatures should be measurable from the ground at those apertures. If any of the nearest dozens of habitable zone candidates carry biosignatures in their air, these instruments will have a strong chance of finding them. The extremely large telescopes are the bridge between the statistical catalog and the first generation of actual atmospheric portraits. The Habitable Worlds Observatory is the mission specifically designed to answer the biosignature question at the scale where the answer becomes statistically meaningful. It is a NASA flagship concept currently in the development phase, with a projected launch in the early to middle 2040s depending on funding and engineering timelines. Its central design goal is to image at least 25 Earth analog planets around nearby, Sun-like stars, and obtain full spectroscopic characterizations of each atmosphere. The mission's coronagraph will suppress starlight by a factor sufficient to reveal the reflected glow of Earth-sized planets in habitable zone orbits around the nearest Sun-like stars. Oxygen, water vapor, ozone, methane, carbon dioxide, and other atmospheric constituents will be readable from the spectra of worlds that today are invisible to every instrument we possess. If the mission launches on schedule and performs to its design specifications, the question of whether any of the nearest 25 Sun-like stars hosts a planet with the chemical signatures of life will be substantially answered within roughly 20 years from tonight. That is not a distant or abstract horizon. It is within the working lifetimes of researchers currently in graduate school, and within the lifetimes of most people who will ever hear this catalog described. The Habitable Worlds Observatory is the instrument the question has been waiting for since the night Kepler 22b first gave the search a specific address to point toward. Several smaller missions will contribute their own pieces to the picture before the flagship arrives. The Plato mission from the European Space Agency, scheduled for launch in the late 2020s, will conduct long-duration transit surveys of bright sun-like stars, searching for Earth analog planets with orbital periods measured in months to years rather than days. The Ariel mission, also from ESA, will characterize the atmospheres of hundreds of exoplanets across a broad range of temperatures and sizes, building the statistical baseline that biosignature interpretation will require. The Espresso spectrograph at the Very Large Telescope, Maroon X at Gemini North, and X-rays at the Lowell Discovery Telescope are pushing radial velocity precision into the range where Earth-mass planets around Sun-like stars become detectable from the ground. Each of these programs adds a different layer of detail to the population picture, filling in the gaps between the headline discoveries and the statistical estimates that connect individual worlds to galactic counts. The cumulative effect of all these instruments operating simultaneously across the 2030s will be a catalog of nearby habitable zone planets far more complete and far more deeply characterized than anything that exists tonight. The named worlds we have walked through will be joined by dozens more, each one a real, specific place with its own atmosphere or portrait and its own particular position in the conditional probability chain. Beyond the instruments with confirmed funding and firm launch dates, a longer horizon of possibilities is taking shape in concept studies and early engineering work. The Ptolemy Small Telescope mission is designed specifically to search for Earth analog planets around Alpha Centauri, A, and B through precision astrometry, the tiny positional wobbles that an orbiting planet induces in its host star's apparent position on the sky. Various proposed space-based interferometers, if funded and built, could in principle resolve surface features on the nearest Earth analog planets, rather than reading only their integrated atmospheric spectra. The most speculative proposal places a telescope at the Sun's gravitational lens focal point, roughly 550 astronomical units from the Sun, where the Sun's gravity bends and amplifies light from distant objects enough to function as a natural telescope of extraordinary power. None of these concepts is a funded mission. All of them represent the direction the field is pointing, the trajectory of what may become possible in the second half of this century if the appetite for the question persists. The shorter horizon, from James Webb through the Habitable World Observatory, is the one most relevant to the question we're sitting with tonight. The longer horizon is the reminder that even the answers the next generation of instruments provides will not be the final answers, only the first ones. The question of direct probes to nearby habitable zone candidates is the one that popular imagination returns to most persistently. And the honest answer is that the timeline is longer than most coverage implies. Proxima B sits for 24 light years away, and the fastest spacecraft humanity has ever launched travels at roughly 150 kilometers per second at its peak velocity. At that speed, the journey to Proxima would require approximately 8,500 years, a duration that makes the question of probe travel a question for a civilization with fundamentally different propulsion technology than the one we currently possess. The Breakthrough Starshot Initiative has been developing the concept of laser-propelled light sails that could in principle reach a significant fraction of the speed of light, reducing the transit time to the Alpha Centauri system to roughly 20 years. The timeline for a first launch, if it happens, is currently mid-century or later, and even the most optimistic scenario, the first close-up data from any nearby habitable zone candidate would not arrive until the second half of this century at the earliest. For the foreseeable future, the question of what these worlds actually contain will be answered by remote observation across light years of space, not by instruments deployed in their atmospheres or oceans. The atmospheres will be read by spectroscopy, the surfaces inferred from that spectroscopy, and the biosignatures, if they exist, will be detected as chemical imbalances in air that has never been directly sampled by anything we have built. The answers that are coming will arrive piece by piece, candidate by candidate, one atmosphere of spectrum at a time, and the accumulation will be slow enough that the question will outlast many of the people currently most invested in asking it. A first confirmed biosignature on any exoplanet, if it comes, will be a turning point comparable to the first confirmed exoplanet detection itself in the mid-1990s, a moment when the second number in the gap changes from 1 to something larger. Whether that confirmation arrives in 2030 or 2040 or 2050 or not within this century is the question the next several decades will answer. The first biosignature will probably be ambiguous, a tentative signal in a noisy spectrum that requires years of follow-up before the field reaches consensus, much as the K2-18b dimethyl sulfide signal has been contested and refined since its initial announcement. The second confirmed biosignature will be less ambiguous, and the fifth will begin to look like a pattern, and the pattern is what changes the conditional probability estimates from speculation into observation. The catalog is in this sense not a finished inventory, but a living one, growing every month as instruments improve and methods sharpen, adding names and atmosphere portraits and chemical signatures to a list that began with a single transit dip in a single star's brightness curve and has been expanding ever since. The named worlds that anchor the catalog are real and specific places that deserve to be held as places rather than as data points. And the closing inventory of them is worth taking slowly. Somewhere in the direction of Cygnus tonight, a possibly oceanic world is tracing its 290-day orbit around a star slightly cooler and dimmer than our own. Whether it has an atmosphere, whether that atmosphere holds anything of interest, whether the deep water beneath it has ever produced anything that swims, all of that remains completely open after 15 years of being the catalog's first entry. Somewhere in Centaurus tonight, a small rocky world is locked into permanent day and permanent night around the nearest star to the solar system. Its terminator a ring of dim red twilight that has held that position for billions of years without any instrument close enough to read what it contains. Somewhere in Aquarius tonight, 7 Earth-sized worlds are resonating around an ultra-cool dwarf that will still be burning hydrogen long after every sun-like star in the galaxy has exhausted its fuel and gone dark. Somewhere in Leo tonight, a hydrogen-skied ocean planet is turning slowly with methane and carbon dioxide written in its atmosphere and the faint possible whisper of organic chemistry that the next several years of observation may either confirm or quietly retire. Each of those places is real, and each of them is there tonight regardless of whether any instrument is currently pointed at it. The honest answer to the question that opened this catalog is a layered one that holds its own uncertainty as part of its content rather than as a deficiency to be apologized for. The galaxy almost certainly contains somewhere between several billion and several hundred billion worlds where the conditions for liquid water exist and where the architecture of star and planet is compatible with biological persistence across geological time. The universe contains them in numbers that translate only into words functioning as placeholders for quantities the mind cannot hold in any felt sense. Whether any of those worlds are inhabited is the question that remains open, and it is open by amounts that span many orders of magnitude and that no current instrument can close. The conditional probability chain from habitable to inhabited to intelligent to communicative could be high enough at each step to fill the galaxy with company we have not yet found, or narrow enough at some single step to leave Earth as the only lit window in a building of almost incomprehensible size. Both possibilities are consistent with everything we currently know, and the silence of the radio telescopes does not yet distinguish between them with any confidence. The next 2 decades of observation will not resolve the question entirely, but they will begin to close in on the biosignature end of it, which is the end most accessible to the instruments being built right now. The catalog that lives between the 2 numbers, between the 1 confirmed inhabited world and the tens of billions of plausible ones, is the most important inventory in modern science, and it deserves to be held with exactly the patience the question itself requires. Most of the worlds in it are dark, most are silent, most will never be visited by anything we build, and most will never tell us whether anything is alive in them. A few of them, in the next several decades, may begin to answer. The preparation the universe has made across billions of years of rocky planet formation, of oceans pooling under atmospheres in the right temperature ranges around the right stars in the right galactic neighborhoods, is real whether or not anything ever takes the offer. The galaxy has been making plausible homes for as long as there have been stars to warm them, and most of those homes have